the Hellenistic civilization, Greece replaced Achaean as the written language for the educated Achaeans. And since then, Achaean mathematics fused with Greek and Babylonian mathematics, which gave rise to Hellenistic mathematics. Mathematical studies in Egypt continues below Islamic Caliphate as a part of Islamic mathematics, when Arabic became the written language of the educated Achaeans. At that time, mathematics also developed rapidly. This happened because mathematical knowledge was indispensable in measuring and making maps, measuring for building construction, etc. In teaching, mathematicians in these fields look for and study numbers, sizes, fields, etc. until some scientists found a way to count and measure the object, then made a measurement or count formula, which was written in an inscription or a roll of paper from papyrus rock, so that in teaching, people who studied it were easier to understand and faster to understand it. Civilization reached a high level in Egypt at an early period. This country was well suited for the people, with a fertile land thanks for the river Nile, yet with a pleasing climate. It was also a country which was easily defended, having few natural neighbors to attack it from the surrounding desert, provide a natural barrier to invading force. As a consequence, Egypt enjoyed long periods of peace when society advanced rapidly. By 3000 before century, two earlier nations had joined to form a single Achaean nation under a single ruler. Agriculture had been developed, making heavy use of the regular wet and dry periods of the year. The Nile flooded during the rainy season, providing fertile land which complex irrigation system made fertile for growing crops. Knowing when the rainy season was about to arrive was vital, and the study of astronomy developed to provide calendar information. The large area covered by the Achaean nation required complex administration, a system of taxes, and armies had to be supported. As the society became more complex, records required to be kept and computation done as the people bartered their goods. A need for counting arose, then writing and numerals were needed to record transactions. By 3000 before century, the Achaeans had already developed their hieroglyphic writing. This marks the beginning of the Old Kingdom period, during which the pyramids were built. For example, the Great Pyramid at Giza was built around 2650 before century, and it is a remarkable feat of engineering. This provides a clearness of indication that society of that period had reached a high level of achievement. Hieroglyphs for writing and counting gave way to a hieratic script for both writing and numerals. The Achaean number system were not well suited for arithmetical calculation. We are still today familiar with Roman numerals, and so it is easy to understand that although addition of Roman numerals is quite satisfactory, multiplication and division are essentially impossible. The Achaean system had similar drawbacks to that of Roman numerals. However, the Achaeans were very practical in their approach to mathematics, and their trade required that they could deal in fraction. Trade also required multiplication and division to be possible, so they devised remarkable methods to overcome the deficiencies in the number system with which they had to work. Basically, they had to devise method of multiplication and division which only involve addition. Each hieroglyphic number can be found of temples, stone monuments, and vases. They give a little knowledge about any mathematical calculation which might have been done with the number system, while this need to develop symbols which could be written more quickly. However, once the Achaeans began to use flattened sheets of the dried papyrus read as a paper and the tip of reed as a pen, there was reason to develop more rapid meanings of writing. This from the development of hieratic writing and numerals. There must have been a large number of papyri, many dealing with mathematics in one form or another, but sadly, since the material is red and fragile, almost all have perished. It is remarkable that any have survival at all, and that they have a consequence of the dry climatic condition in Egypt. Two major mathematical documents survive. We can see an example of Egyptian mathematics written on the ring papyrus and another papyrus like Moscow papyrus with a translation into hieratic script. So here is the Rain Papyrus. The Rain Papyrus is named after the Scottish Egyptologist Henry Reid, who purchased it in Luxor in 1858. The papyrus, a scroll about 6 meters long and 1/3 of a meter wide, was written around 1650 before century by the scribe Ahmed, who states that he is copying a document which is 200 years older. The original papyrus on which the Rain Papyrus is based therefore dates from about 1850 before century. The very long Egyptian mathematical text, the Rain Gazette, sometimes referred to as the Atmas Gazette, it's dated to 1650 before century, but it's probably a copy of an older Middle Kingdom document. The sheet is an instruction manual for students of arithmetic and geometry. In addition to providing areas, formulas, and methods for multiplication, division, and working with fraction, the sheet is also evidence for other mathematical sciences, including composite numbers and prime, arithmetic, geometric, and harmonic average, and simple understanding, Eratosthenes' shift, and perfect number theory. That is, the sheet also contains how to solve linear equation first order, as well as arithmetic and geometric sequences. Also, the three geometric elements inscribed in the Rain sheets imply a very simple discussion of analytical geometry. First, how to get approximation which is less than 1% accurate. Second, the old atom to square the circle, and the last one, the third, the earliest used cotangan. And the next one, here is the Moscow papyrus. Now, it is now becoming more common to call the Rain Papyrus after Ahmed rather than Rain, since it seems much fairer to name it after the scribe than after the man who purchased it comparatively recently. The same is not possible for the Moscow papyrus, however, since sadly the scribe who wrote this document has not recorded his name. So sad, right? It is often called the Golenistu papyrus after the man who purchased it. The Moscow papyrus is now in Museum of Fine Art in Moscow, while the Rain Papyrus is in the British Museum in London. Another important Egyptian mathematical text is the Moscow sheet, also from the Middle Kingdom era, that to 1890 before century. This manuscript contains word problems or story equations, which may be intended for entertainment. One problem is considered to have special needs because it provides a method for obtaining volume pyramid beheaded. If you were told a cut pyramid is 6 units long, 4 length unit below, and 2 length unit above, with u square 4, which equals 16, u double 4, which equals 8, you square 2, which equals 4, and you add up 16, 8, and 4, which equals 28. You can take 1/3 of 6, which equals 2. You can take double of 28 twice, which equals 56. So behold, the result is 56. You got the truth. Finally, the Babylonian tables show that the ancient Athenians were able to solve second-order algebraic equations. The Rhind papyrus contains 87 problems, while the Moscow papyrus contains 25. The problems are mostly practical, but a few are posed to teach manipulation of the number system itself without a practical application in mind. For example, the first 6 problem of the Rhind papyrus asks how to divide n loaves between 10 men, where n is equal to 1 for problem 1, n equal to 2 for problem 2, n equal to 6 for problem 3, n equal to 7 for problem 4, n equal to 8 for problem 5, and n equal to 9 for problem 6. Clearly, fractions are involved here, and in fact, 81 of the 87 problems given involve operating with fraction. Rising, in these cases, there are problems of fair division of loaves, which were particularly important in the development of Athenian mathematics. Some problems ask for the solution of an equation. For example, problem 26, a quantity add to a quarter of that quantity becomes 16. What is the quantity? Other problems involve geometric series, such as problem 64. The problem is divide 7 hectares of barley among 10 men, so that each one get 1 per 8 of a hectare more than one before. Some problems involve geometry. For example, problem 50. A round field has diameter 9 cat. What is this area? The Moscow papyrus also contains geometrical problems. Unlike the Greeks, who thought abstractly about mathematical ideas, the Athenians were only concerned with practical arithmetic. Most historians believe that the Athenians did not think of numbers as abstract quantities, but always thought of a specific collection of 8 objects when 8 was mentioned. To overcome the deficiencies of their systems of numerals, the Athenians devised cunning ways around the fact that their numbers were poorly suited for multiplication, as is shown in the Rhind papyrus. Now, we examine some claims regarding mathematical constants used in the construction of the pyramids, in particular the Great Pyramid of Giza, which, as we note above, was built around 2650 before century. We give some measurement of the Great Pyramid, which makes some people believe that it was built with certain mathematical constants in mind. The angle between the base and one of the faces is 51, 50, and 35 darjat. The second of this angle is 1,61806, which is remarkably close to the golden ratio 1,618,034. Not that anyone believes that the Athenians know the second function, but it is of course just the ratio of the height of the sloping face to half the length of the square base. On the other hand, the cotangent of the slope angle of 51, 50, and 35 is very close to P per 4. Again, of course, nobody believes that the Athenians had in fact the cotangent, but again, it is ratio of the sides which is believed what made to fit this number. That is my explanation about development in Athenian mathematics. Thank you for your attention and thank you for watching.